So postulate 3 says collisions result in no change in energy and the average kinetic energy depends only on temperature. So all collisions between particles and with their container are elastic. So that means that there's no gain or loss of energy. Imagine you're on a trampoline where you don't have to put in any effort and it just bounces you exactly how high as you were. That's what we're going to assume for kinetic molecular theory. We're not going to assume that you start bouncing and slowly come back to Earth like a basketball or something. We're going to pretend that you're just going to bounce right as high as you came each time, so you don't actually lose any energy when you hit stuff. There's a nice little basketball to illustrate that. But here, we see that they're not actually slowing down over time. They're just going to keep moving and keep their same amount of energy until you like increase or decrease the temperature. Collisions must be elastic. So this is another way to think of the basketball. Think about you have an inflated basketball. Does it slowly, I know obviously over like a year or two it's going to deflate because like little holes and stuff, but just if you leave a ball for 5 minutes, it's not going to slowly go back to being deflated because the particles lose energy. They're going to keep hitting the edges of the ball, but keep hitting them with the same energy to keep the ball inflated. That's what we mean here. We're going to keep bouncing back with the same amount of energy and keep things inflated and keep gases moving the same way, even though they're hitting the walls of their container. So here's some extra stuff, which isn't going to be the main focus of our unit just because we're doing it a little bit condensed because we're doing it online. But I'm still going to show you because it's quite important and interesting. But we have intra and intermolecular forces. So intra means inside or within something. So that's like a bond between oxygen and hydrogen and water. And intermolecular forces are attraction between different molecules, like how we have two sodium molecules becoming attracted to each other, or like a hydrogen bond here. So all that I really want you to take away here is to consider that there's intermolecular forces, which go between different molecules, and there's intramolecular forces, which happen inside of a molecule, like a bond. So just take a second and pause it here to visualize this. This is just wording that we may use moving forward, but it's not the main focus here. One thing to note about gases is they don't really have intermolecular forces in the same way. Solids and liquids are held together much stronger. Gases are typically free to just kind of, as it says here, to whiz by each other. So the last postulate is there are no forces of attraction between particles or the container. So this is where we're going to put a disclaimer. You'll see this in your booklet too. You're going to have notes about this. But kinetic theory assumes that all gases behave ideally, but we know this is not always the case. So when we talk about an ideal gas, and you may have heard in like your whole 22.4 liter thing, we're saying that's for an ideal gas. So we're imagining a gas is completely perfect and doesn't ever interact with anything. In reality, that's not the case, but for KMF, or kinetic molecular theory, sorry, for KMT, we're going to assume that it is. So ideal is no forces between each other and all straight paths. In reality, we're going to see little bits of attraction between gases where they curve a bit and affect each other, but they're pretty small, and for our purposes, we're just going to assume that they're not interacting and that they can travel straight. So gases are easy to diffuse because of this. They just kind of move apart from each other and don't have the same attractions as solids or liquids. There can't be much attraction between gas molecules normally since particles expand out and diffuse easily. This makes sense. Like if you think of a solid, it's not going to come apart the same way a gas would. If you open up a can of sardines, you can smell the gas everywhere, but the sardine itself isn't like moving all around the room. So here's just a review of kinetic molecular theory for gases. It is easily compressed with low densities. The particles of a gas must be far apart and loosely packed. There is no fixed shape and no fixed volume. The particles are in free, constant, random motion involving elastic collisions, meaning they retain their energy. And they are easy to diffuse because the intermolecular forces, or the intermolecular attraction, is weak, and the particles have no restrictions accordingly. So we've talked a lot about gases up to now, and that will be our unit next week, but for now we're still going to think about solids and liquids. So I invite you to pause this video for a second and think about how this might be different. These same 3 points, but how might they be related differently? liquids and solids. Take a second here, pause the video if you like, and just think about how these might look different for a liquid or for a solid. Okay, I'm going to move to the next slide in a second, so pause it if you'd like to take a second to think. Okay, so kinetic molecular theory for liquids. Liquids are hard to compress and more dense than gas. Particles are closer together and more densely packed. So what we're saying here is that liquids, you can't just like squeeze them down. As much, if you think about it, it's harder to move through water than air, and that's what we're saying here. Liquids just have a bit more force holding them together, and there's more particles in a smaller area. They have no fixed shape but definite volume. Um, the intermolecular forces are strong enough to allow some particle movement but limit their distance. This means that water, or like a liquid, let's say you take a bottle of Coca-Cola, it's always going to be that 300 or that's a can. It's always going to be that 591 milliliters. But if you pour it into a bowl, it'll have like a wide flat shape, and if you pour it into a really thin vase, it'll be like tall and skinny. So we have the same amount, so a definite volume, but we don't have a fixed shape. And they're fairly easy to diffuse. So intermolecular attraction is stronger than in gases, restricting particle flow, but it can diffuse. Liquids can especially diffuse in one another. If you mix in like Kool-Aid to water, you'll see it spread around. So these are just kind of a middle ground between solids and gases, as you can see here. I recommend making a chart to kind of compare all these. There's one sort of like that in your notes that you'll fill in too. Lastly, for solids, they are hard to compress with high densities. Particles are very close together and very densely packed. Imagine you take like a penny. It's pretty hard to squish it any more than it is, or if you take like a mug, or if you take your pen. They're very densely packed and very, very well held together. They're not just floating off into space. They have a definite shape and definite volume, so no matter what container you throw the pen in, it's still going to be shaped like a pen. If you put your headphones inside a water bottle or you put them inside a bowl, they're still going to be the same shape. They have the strongest intermolecular forces that severely restrict particle movement and control the distance between particles. They are not easy to diffuse because they have the strongest intermolecular forces completely restricting particle flow. Quite literally, solids are solid. They're not going to just be letting their molecules float off and get away from them because they're very attracted inwardly. They have very, very strong intermolecular attraction. So solids come in two main forms, crystalline and amorphous. You'll see this a bit in your notes as well. So crystalline are arranged in geometric three-dimensional pattern. Don't worry about all these, but just kind of to see them. They can be like cubes. We call this a lattice. They can be like in different shapes. They can have more things in the center. So yeah, they can be like that, or they can be amorphous and have irregular shapes like glass or quartz or something. That means without form in Greek. So that's you can see here we can have crystalline quartz, sorry, and that would be like when it's arranged nicely, and then glass can be amorphous and kind of take the shape of anything. So that just about does it. We're just going to end on by saying that solids are held by ionic attraction or covalent intermolecular forces. This isn't going to be the main focus, but just what I want you to remember is intermolecular forces are strongest in solids and weakest in gases. So the main takeaway from today are the postulates and then these lists of kinetic molecular theory for solids, liquids, and gases. So I'd like you to make note of all the postulates in this presentation and the kinetic molecular theory as it relates to solids, liquids, and gases, and then try the worksheet that I'm posting today. Then tomorrow we're gonna review the worksheet and the work and get you all ready to do a little assignment on Thursday. Yeah, that's all for today, chemists. I hope you enjoyed this lesson and I hope you have a lovely day.